What's up, guys? Kristen Ninja here, and welcome back. Study sessions. Let me see exactly. Okay, cool. Awesome. So, welcome back to study sessions. I'm your host, Kristen Ninja. And if you're here, that means your goofy self waited until the last minute to study. Or your non-goofy self wants to get as much studying in as possible before, the end of the or before you have to, s- stop studying and take the test that's tomorrow. Either way, I got you covered. So, I heard from a good friend of mine that ESET 355 is starting it's going to be doing their first exam. And so, since they're doing their first exam tomorrow, I just wanted to give y'all a little bit of a little quick review. Um, that may help. Hopefully, it does help because I know that class was a little bit more difficult for me. Some of y'all are probably a little smarter than I am. Some of y'all maybe not, but that's okay. That's all right. Um, the important thing is that you're in the class, you made it this far, and I have faith in you that you can do it. Um, so with all that being said, going over a couple AC concepts that I'm sure the wonderful professor that teaches this class has probably taught you before. Capacitors store energy. The other thing that he didn't mention, because we don't really work with inductors all that often um, in this class, or you will probably not work with inductors all that often in this class, is that inductors those store current. So stores um now I'm not going to be doing a lot of calculations today just because I'm just giving y'all like an idea of like how to do stuff. But if you wanted to know the calculations, check your homework, go back over the homework for this class, and you'll be fine. Also, in my other study live streams that I did a few months ago when I was going over 355 stuff again, that has more calculations. So go check that out if you want to see like actual calculations and stuff and how some of that stuff is done. Um, so there's you need to know what epsilon is. Epsilon is permittivity. Um, I can never remember which one is which. I mean, I guess you could remember like epsilon is permit, like permet, like like I don't know, and permeable. I mean, I don't know. It's permittivity and permeability. Permittivity is epsilon, and that value, which I will rewrite here, is epsilon naught times epsilon naught equals 8.85 times 10 to the minus 12. That typically deals with capacitance, so this would usually be in farads. Um, yeah, so inductors they store current. So the reason we typically use capacitors is because at a DC or direct current, no current really flows through. Now, if you put a capacitor in in a circuit and you with a battery and you test it like that, you'll see a little bit of something because there's always a little tiny bit of noise or something like that. So that's how some of that stuff ends up working out. And as long as there's another way to like have the circuit discharge um, around the capacitor, then it'll charge up on one plate and then discharge slowly across like but it's very 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 slow. But the reason we use AC signals for this is because since a capacitor has to charge up on one side, so we'll say it like blue is T equals 1, the energy is flowing this way, and it charges up the capacitor here. And then green is T equals 2. And then when the signal flips to T equals 2, the signal is coming this way, and the charge goes up here. So what ends up happening is that the charge here, when it flips to time 3, it dissipates and goes around back to here. And then at time 4, it will dissipate from here and go back around here. And that's how you get your current flow. So um, that's just to illustrate that. I'm sure you already know this, but I'm just going over the basics. Um, for an inductor, wow, I really, really need to work on my writing. Um, for an inductor, ZL equals J omega L. Omega is almost always 2 pi F. So if you ever have something with omega in it, if you find 2 pi F, you will probably be fine. Um, here's a little rule of thumb that I made up that might help you remember if you're asked like what is a short at high frequency or low frequency. Uh, at a low frequency, an inductor is a short. Its symbol is an L, so L low short. There you go. A cap is at the top, like a cap on your head. So at a high frequency, it's a short. That's an easy way to remember it. Let's see. So with inductor, inductors create a magnetic field, so you can find L using mu n squared. N is the number of turns of the inductor multiplied by the area of the inductor, that's cross-sectional area, divided by the length of the inductor. So I think somewhere low frequency, high frequency. Yeah, so this is just like the same thing that I said a moment ago. Um, yeah, so this is how you can find inductance right here. So if we had like, let's just say our mu value was 2, and also keep in mind that mu is never just mu. So let me actually write that so y'all can remember. Mu is never just mu. It's mu naught times mu r. Now mu naught, we're assuming that we're working with air or we're working with a mu r of 1. So most times mu r equals 1. Now that doesn't mean it's always going to be that way. So if you're looking at a question on the exam and it's like mu r equals 3 or mu r equals 1.7, pay attention to that because you got to multiply that along with your mu value. And mu, oh yeah, I have it written up here. So mu is mu naught times mu r. Let me just rewrite that, make it cleaner. And then mu naught equals 4 pi times 10 to the minus 7 henries per meter. And mu r is about 1 or almost always equal to 1. So that's That's what I'm saying right here. Um, so let's just say that mu in this case comes out to where mu naught times mu r equals 2. So we'll just say for example sake, mu equals 2, n equals 2, a equals 8, and L equals 10. So we would have 2 times 2 squared times 8 all over 10, which gives us, that's 4, 8, 8 times 8, 64, 64 over 10. That gives us an inductance of 6.4 henries. So that's just an example. I'm using big numbers like this so I can show the calculations without using my calculator. But you will not have numbers this clean on the exam. So please learn how to use your calculator. I would highly recommend. Now, this is a recommendation. It's just a recommendation. If you can remember at the beginning of the exam, after, of course, you've cleared your calculator, before on the exam, like before you start, take about an extra 10, 15 seconds and put in mu naught and epsilon naught into your calculator. That way, when you have to solve for them, you don't have to remember exactly what numbers they are. Just store them in your calculator. And you can do that by putting the number you want, store, and then store it to a letter value. So like maybe E or U or O or something like that. Something that you can easily remember. So when you call it back, you can do like if it's like find the permittivity of this capacitor at epsilon r equals 1.31, and then you just do your whatever you save your epsilon as, multiply that by the 3 1 and blah 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 blah, and then bam, what a bam, thank you, ma'am. You get permittivity. So that's one thing that I would recommend doing. I did that for my exams. I had my numbers written in the calculator right when I started the test. I took a moment, put the numbers in my calculator, and then when I was taking the test, I didn't have to remember those numbers. I just had to double check that they were correct. So that's also a thing that you should make sure you do. Make sure you memorize what numbers they are, because if you mistake permittivity for permeability and you put 4 pi times 10 to the negative 7th, your answer is going to be completely wrong unless you're working with both in the same equation. So remember the numbers carefully, and to save yourself time from typing it in, store the number like right when the test starts. Give yourself like take an extra 10 seconds, store the number. It'll save you time in the long run. Let's see the impedance, reactance, and phase. Shout out Dr. Hudson. Appreciate you. If you didn't take ESET 211, you missed out on a wonderfully taught class. I mean, like, it was a fun class to be in. And I remember a lot of the stuff from that class very well because it was something that I couldn't really, I don't know really how to describe it, but I remember some of that stuff in that class so well because it was just ingrained in us. Reactance and phase, 707, 637, like things that I would actually need as an engineer. And this is stuff that I'm giving y'all to help to like kind of give back to the ESET community. So this is just like again, this is a study session. It's not me giving you answers. It's not me giving test help or any like any see. I'm not in cahoots with any of the professors. I don't know what's going to be on tests. All I know is what I do. Um, and these are all my handwritten notes. This is from professor's class, but these are all the notes that I wrote. So this is my stuff. Um, some of the numbers are his, but like some of the numbers like from the examples are his, but I'm making up my own examples as well. These are used as a reference, but anyway, that's not really that important. Um, the reactance of a capacitor, as you know, 1 over j omega c. Uh, You could say J times -1 over omega C, but in general, the reactance XC equals -1 over 2 pi FC. Like I said, omega is almost always 2 pi F. And this comes into play, this will come into play when you're working with Smith charts. Hold on. I gotta like this will come into play when you have to work with Smith charts. You need to know what the J value is, which is the imaginary value. So you'll have so you have I don't like how it's denoted because it makes it feel like it's not real, but it is real. It's just called the imaginary plane because like we can't I'm going to call them fourth dimensional numbers. This is a fourth dimensional number. So you sitting in your room right there, how I'm breaking the fourth wall? Yeah. I see you eating them potato chips. Yep. Mm-hmm. And now you're drinking your drink? Mm. What the hey, those the sour cream ones? My kind of person right there. Hey, make sure you get some water too. I see it sitting right next to you. Grab that water bottle. If that ever actually lines up with somebody's life. But anyway, fourth dimensional number. So that's what I'm going to call these now. So we're going to say fourth dimensional numbers. So with fourth dimensional numbers, our world is in 3 dimensions. I'm sure you've seen the thing where like if you have someone in a 2D world, if you have someone in a 2D world and you try to show them, a sphere, all the person is going to see is basically a circle that starts small, gets bigger, and then gets smaller again. So that's like the definition of like being outside of the realm of your own dimension. Um, so because we can't really perceive time, like we can perceive time passing, but we can't perceive time changing. When you have a phase shift of anything, it typically a phase shift is just well you probably know if you took 211, but a phase shift, you know that's the first phase, and then that's the second phase. Oh wow, they're not exactly the same, but you know that's what a phase shift is. It's shifting left or right. Let me actually write this neatly. So a phase shift is shifting left or right from a reference time point. Anyway, fourth dimensional numbers. To get now that y'all have like a grasp of what I'm trying to say, I can get to the fourth dimensional number part. So when you have a phase shift, you have to write it in a phasor form, which typically ends up being this is I think this is actually something that you're going to be tested on as well. Phasor forms, and you need to put it in, I believe, polar form. So there's rectangular form and there's polar form. Rectangular form is like some impedance. So we're just gonna put like some impedance in the real domain plus an impedance or plus or minus of impedance in the J domain or fourth dimension domain. Now, if we were to plot this, if let's say we had if we had a resistor, so we'll pick white as our real values. If we had a resistor that had like 20 ohms, so we'll just say like this is 20 ohms. This is where it would sit. Resistor has only real values. A capacitor with reactance, we'll do the capacitors and inductors in blue. A capacitor with reactance, since it's 1 over J, as J increases, the number gets smaller, so you can see how it would go down, right? So we have negative 20 ohms of impedance from a capacitor. So now we have minus 20 J in the J direction. This is 20 in the real domain, but that's given, like real is assumed, so you don't have to put the R there. If we had an inductor, as J increases, the number increases, so you would go up. So you'd have 20 ohms in the J direction, but that's plus 20. That's where that comes from. So when you're writing in rectangular form, this is the rectangular form. Yes, this is rectangular form. In polar form, it's typically written as the total impedance. So it's like Z multiplied by a phase angle theta. Theta is almost always in degrees, but the way Bosshard teaches his class, and I think actually just the way that you have to learn high frequency signals in general, everything is going to be in radians. So learn to convert from degrees to radians. So my simple trick that worked most of the time for me, take it if you want, don't take it if you don't want. If you're in radians and you want like if you're in radians and they're giving you radians or you know how many radians you need or something like that, take your number. So let's just say I have a one radian or something like that. Or actually, you know what? Let's just say pi, because pi is pi over two. So sine of pi over two. Sine of pi over two z. That is 90 degrees. But if I needed to get back like in radians, I would just do sine of pi over two. That equals sine is the y. So that equals 0. Then change my calculator mode to degrees. And then do minus sign or inverse sign, not minus sign of 0. And that should give me 90 degrees. Now let me double check and make sure that works because it's something very, very similar to that. I'm just picking something that's easy to work with. So sine of pi over 2. Oh, hold up. So if I'm in radian, sine of pi over 2. Oh, my bad. It's not 0. It's 1. I get conf. Oh yeah, that's right. It's the y value. Sometimes I'm sorry, y'all. Sometimes I get a little confused. Sometimes sines and cosines are a little bit confusing at times. Sometimes they're a little confusing. My bad. Not 0, 1. Um, but yeah, so sine of pi over 2 is 1. Then I do the change of mode, go to degrees, and then do the arc sine or the inverse sine of 1, and that gives me 90. So you can see that hopefully right there. So that's a way you can quickly convert from degrees to radians to degrees, sine the value, inverse sine, or cosine the value, inverse cosine, whatever. Um, But yeah, so when you have that, you'll end up having your rectangular form as z plus j plus or minus j multiplied by the reactants. It's not necessarily z, it's just the reactants. Let's see. Let's see what else I can see what else I can cook up for y'all. Let's see. What under my eyes, they go. Okay, so transmission lines. Transmission lines are another thing that will be on the exam. Um, so if you have a 50 ohm load, you have a transmission line, your R naught value is the resistance in that transmission line. That typically does not change. You might have some battery voltage there, but you just have to basically do a voltage divider and find that. So for this, man, I honestly could rewrite these notes and make them look nice. Where's my time? How is this? Hold up. Oh, circuit behavior. Let me get to the circuit behavior first. So circuits, sorry about that, y'all. Circuits change with their outside factors. So as frequency, as as f becomes larger, I'm really going to rewrite this. The inductor holds a current, so that's that Z equals J omega L. Um, as frequency increases, a capacitor or a cap acts like a short circuit. Now I know you're probably thinking like, bro, you said that like 5 times already. I want you to remember that because it's something that will actually matter. Um, so real world effects have a problem. Like real world effects, they affect stuff. So for even for a wire, um, so as we all know, every every electrical everything has some type of resistance. That's why electricity can flow anyway. Like for example, pure water. I'm talking pure water with no ions in it at all is not conductive. As soon as something is introduced into the water that can make it ionic, that gives it some type of path that a charge can follow through, that's what gives it the ability to charge. So to have absolutely zero resistance would be the same thing as having something that does not allow charge, because as we all know, V equals IR. Without any resistance, there's no current flow. Without any current flow, there's no voltage drop. Simple as that. So therefore, even wires with zero resistance have some tiny resistance. Just saying. That's why racist. That's why at if you were to have This explains short circuits very well, actually. So V equals I R. V equals IR. If my resistance is like 0.0000001 ohms, and my voltage is like just let's just say 2 volts. How much freaking current am I going to have to drive through that wire to get to 2 volts? So you do 2 divided by 1 micro ohm, and that gives you a current that is absolutely massive and very dangerous. That's why short circuits are dangerous. That's why, because that amount of current will burn through everything. You will not have, like, there will be barely anything left with that amount of current running through something. It's going to be hot because current creates power, power creates heat. So, anyway, the real resistance of a wire is R equals the length of the wire. That looks like the little breast cancer awareness sign symbol, except in blue, but it was supposed to be an L. So real resistance of a piece of wire, the it's the length divided by the what is this? I think this is the resistivity of the material multiplied by its area. So um copper's happens to be 5.8 times 10 to the seventh uh ohms per 1/ohms per meter. Oh, geez. What in the cheese? What in? Okay, cool. Cool. We're good. We're good. Um, and um, that will give you this R value here at the resistor here. So this is R. Let me change this down to a smaller pen size. That's R. The inductor, L, you need to find the impedance of the inductor or the inductance of that wire. Now, the inductance can change with frequency. However, it basically doesn't matter with a wire because it's so low. It's so low. But you can find that inductance or the impedance. The inductance has to do with the length of the wire, but you can find the impedance of that. You can find the impedance of L. Let me just rewrite this. Impedance of L using mu naught. Remember, not epsilon naught, but mu naught. Now, if y'all remember, what is mu naught? Exactly. 4 pi times 10 to the next. You see, yeah, I knew you had it. I knew you had it in you. You got this. Let me just double check the stream, make sure that there's no one asking questions. No one asking questions on you not remember. Oh, appreciate you, Cyan, for joining in and the compliment. I'm um just trying to be helpful, you know. But anyway, if there's no questions, let me just reply real quick. Um, take the natural. So you have your permeability. Remember, mu is permeability. I'm just gonna rewrite it for y'all because what I know one of y'all is gonna forget. or one of y'all is probably more forgetful than I am, and you're not going to take my advice and put it in your calculator at the start of the exam or memorize it so you can put it in your calculator at the start of the exam. Look, man, all I'm saying, follow your professor's rules. If your professor says delete everything that you ever worked on in your entire life before the exam starts, delete everything you ever worked on in your entire life before the exam starts. If your professor says open book, open note, open everything, open internet, it's open book, open note, open everything, open internet. Hey, professors can grade and test however they want to. And if you have a teacher that's teaching you how to do high frequency electromagnetic systems and waves, and you get like a whole day to take the test, I hope you know where you're coming to. If you found this video, if you found this after you got like a 10 on the exam, tune in next time. Maybe you'll get an 11 next time. I'm joking. I'm joking. You'll be fine. You'll at least get a 12. Anyway, anyway, remember, mu is permeability. What is my teacher's name in high school? It was wasn't Mr. Leon, was it? No, it wasn't him. I forgot who my teacher was. It was this black dude. He taught at KCal. Oh man. He probably thought I was so dumb because I had never taken any physics classes before I got to physics C. And I was like, what does this symbol mean? What is this? Is this a constant? What do you mean it's a constant? Is this a number? What number is it? Shout out to my man, Dr. Akimov. Appreciate you, my man. You're never gonna see this video, probably. But if you ever see this video, Dr. Akimov, shout out to you. Don't panic mechanics. Knocked all that questions right out of me. I now realize that symbols are just symbols and keep them as symbols until they give you a number to replace the symbol. But like keep them as symbols as long as you can because it makes the math so much easier. Anyway, um, so you take mu naught, which is your 4 pi times 10 to the negative 7, multiply that by the length of the wire, which should be given as L. So I mean, like L is just the length of the wire. Divide that by 2 pi. Now, all that gets multiplied. All that gets multiplied also by the natural log of 2 times the length over the radius of the wire. Jeez, I gotta sneeze. Sorry, y'all. Thank you. Over the radius of the wire. And then you multiply that by, I don't know why it's 0.75. Just trust me on this. I just trusted my professor on this. It worked out pretty well. 0.75. Now, keep in mind that length, that cursive L is the same length on both of the parts of the equation. It's also the same length as the R equation. So length is not changing. You're not trying to solve for two different lengths. So, I mean, if you want to save L in your calculator while you're doing the problem and then just multiply 2L, I mean, who's going to stop you? I'm not going to stop you. Your teacher might if he realizes you done got too much knowledge and you out here acing tests that you may not have learned before, but it is it is what it is what it is. Anyway, so actual components. I'm doing pretty good on time actually. Like I got a good 50 minutes before I need to like shut everything down. Um, Actual components, resistors, wire round for fill. Oh man, I can talk engineering all day, but as soon as it comes to English, third grade reading level. Resistors, wire wound. Let me rewrite that for y'all people that can't read Ninja's script. That's what we're calling it. We're calling it Ninja script because it's a coded message on its own. wire wound. You have film resistors. There could be carbon film, metal film, but in general, we could just say film. Carbon, metal, others. And then I believe I was trying to write composition. I'll also say composite because that's probably what I was trying to say anyway. Sorry, y'all. I went to the gym. I guess like when I was outside, that pollen got to me, bro. I'm telling you, pollen got to me. So the resistor equivalent circuit looks like this. So since a resistor is wire wound, essentially what happens, um, essentially what happens is I'll draw this in green right next to it. When you have a wire wound resistor, so you have like some type of like something that's the wires wound around, and you have circles going around it like that. Now that may look like an inductor, but I'm not trying to draw an inductor. But the point I'm trying to make is that in between each of these wires is basically a capacitor. It's basically a capacitor, and like it's all capacitor. It's capacitors in parallel. And if you remember anything from like my other study streams, capacitors in parallel add like resistors in series. So that's why there's only one capacitor here. It's all added up. Um, and a capacitor is defined. This is like the actual. Well, it's not actually the definition of a capacitor. Oh, actually, let me not say anything stupid. I don't think this is the actual definition of a capacitor, but a capacitor can be defined as this. Two pieces of metal with a dielectric in between. Now, you might be wondering where the freak is the dielectric? I just see green lines. Air is a dielectric. Therefore, what do I got? Therefore, technically speaking, this packaging right here is a capacitor. If I were to run a current through this, I could charge up one side of this. There's a, I mean, if I take the glasses lens out of this and I just seal it back up and have two plates plus air, two pieces of metal, because I mean this is an aluminum packaging. Two pieces of metal, dielectric in between, capacitor. Bam. Um, Technically speaking, you put a piece of metal on one side on either side of your head is now a capacitor. Dielectric is your whole face and moving on. Um, but yeah, so um, the L of so you have a capacitor and a resistor. L is the inductance due to the leads because we learned that wires have some inductance. Um, Let me rewrite this part. Most of the time, the inductance of a capacitor can be neglected. Um, for wire wound resistors, L is a lot larger. Um, it is important to note that let me actually rewrite this whole thing. Resistors, write this in blue, can pick up stray magnetic fields? Due to inductance. So inductors, so resistors can pick up a stray magnetic field due to the inductance, but generally that gets worked out. So um, resistors are basically chilling. Two wires, any piece of wire has inductance and resistance. Any two wires have a capacitance in between them. This is exactly what I was saying right here. Um, two pieces of metal, two pieces of metal with a dielectric in between. That's what two wires next to each other end up being. So ideally, you would just have two pieces of wire, doop, 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 you know, light work. But what actually happens is you have some inductance, some resistance. These are in parallel, so there's capacitors all along this in parallel. Those add up to one capacitor at the end. So you have an L, resistance, resistance, and a capacitance in between. The capacitance between two wires can be found as what is this? I should write this in a lighter color. Looks like pi epsilon L over the natural log of D over R. So I just rewrote this to make it cleaner. Um, as you can see here, the distance, that's D. R is the radius of the wire, I believe. And then L is the length of the wire. There you go. So now it's a little bit easier to read now, hopefully. And keep in mind this epsilon, it's not just epsilon naught. It is not just epsilon naught. Say it with me, y'all. Epsilon naught times epsilon r. There you go. So you see, I knew y'all were smart ones. You're watching the Krista Ninja live stream. Of course you're smart. The second smartest show in gaming slash YouTube. Matt Pat. You could have had electrical theory or something as your fourth channel. I could have. Hey, it's just a theory, but it's not really a theory. It's just electrical engineering. I'm gonna miss you, man. Moving on. So just remember it's epsilon naught times epsilon r, and that's what equals epsilon. Um, so you got the resistor equivalent circuit, yeah. So I redid this because I was trying to study last week or last semester. So this is two wires. Let's see. Capacitance got categorized by a dielectric. Oh, geez. That is some, oh, man. I'm glad I didn't try to share my notes with anybody last semester. Golly. Oh, man. I really enjoyed having Boss Hart as a teacher, but that man talks so fast sometimes because he just wants to teach everything that wants to teach everything he can in the small amount of time that he has. And I don't blame him. That man gave us every single second that we paid for. So shout out to Dr. Bosshard. Appreciate you, my man. Man, I wish he taught an easier class so I could just enjoy having him as a professor. I'm being kind of, if I'm being completely honest, I kind of miss him a little bit. Yeah, my lungs. Mm. Um. Anyway, class categorized by the dielectric material used to make it. Mm. Um, an actual capacitor has resistance and inductance as well. So let me pick a. Oh, didn't change the color. Okay, cool. So I'll say action. If I could spell, gosh, bro, can I write neat? Actual caps have resistance and inductance as well. That's because their leads are also made of wires most of the time, unless of course you have a surface mount capacitor, but we're not talking about surface mount capacitors in this class. So you will have some lead resistance, inductance, and there's actually a bridge between these two. So there's an R1 and R1 and an R2. And I ain't talking D2. I'm so sorry. Um um y'all finna unsubscribe. Okay, so this over here, I'm just cleaning this up so like y'all can read it. Parallel leakage resistance is a function of the resistivity of the dielectric material. So proper grammar. So it's a function of the dielectric material. Um, R1 is equivalent to the equivalent series resistance, and that's a function of the diff. It's a function of the dissipation factor. So this is like kind of how it looks. So there's a self resonance of the capacitor uh, due to the inductance. So at a certain point, um, all that's saying is at a certain point, the capacitors and inductors have a resonance frequency. So if you have a capacitor and an inductor in the same circuit, so just as a quick example, um, I'm sure most of y'all know this already, but like if you're if you're in 355, you probably know this, but if you're taking this as like a supplemental course, like let's say let's say for some reason your department chair decided that, oh, I don't think this ESET class is necessarily important for you to learn at this point in time. And you're like, dog, what the juice? I have no idea what the heck I'm doing in this other class. This is for you. This is for you. So pay attention. Also, if you're like, oh man, I go to a school that's not as big as Texas A&M, or I go to a school bigger than Texas A&M, but they don't care about electronic systems as much, and we only have electrical engineering. I don't know what my teacher's talking about. No resonance frequency. I don't know what they're talking about. I'm here for you. I got you. This is for y'all. So anyway, as a quick example, resonant frequency. So let's just say I have have some circuit, and I have a capacitor, and I have another well, let me draw it this way because this will make more sense to me. I have an inductor. I have I have and a capacitor. Okay, cool, whatever. Nobody cares. We have an inductor and we have a capacitor. Let's just say the inductor, uh, I mean, 15 millihenry, 15 millihenry inductor, and like a 3 picofarad capacitor. Now, we know so resonance is when the reactances match each other. So if we have the reactance of an inductor equals 2 pi FL or omega L times J, and XC equals 1 over 2 pi FC or negative J over 2 pi FC. At some point, when we're finding the resonance frequency, we want to find when 2 pi FL equals 1 over 2 pi FC. And I forget what it is. So I'm just gonna solve for F in this instance. So gonna multiply both sides by F, multiply by F, 2 pi F squared L equals 1 over 2 pi C, divide by 2 pi, divide by 2 pi. Well, 2 pi will then come up to the top, so you'd have 2 pi over 2 pi, um, or 2 pi over 2 pi C. Let me double check that because I don't. Oh geez, almost dropped it. Oh no! Oh no! Oh, okay, we're good. I thought I almost lost my marker. I just want to double check something real quick. So 1 divided by 2 pi divided by 2. Oh, right. Okay. Um, Oh, my bad, y'all. My bad. Dividing by 2 pi. You end up just getting 1/4. So pi. 1/4 pi. Yeah. 1/4 pi because these multiply together in the bottom of the denominator. Uh oh yeah, because we're doing the yeah. Okay, cool, cool. I had to think for a second. Sorry about that. Um I don't have to do a ton of algebra, so I have to be very careful with my algebra when I do it because I will make mistakes if I don't think about it slowly enough. So f squared L divide by L. So now we have 1/4 pi LC equals f squared. We want to get f by itself. Square root, square root of 1. Well, this breaks down to the square root of 1. And the square root of 4 pi squared. That's also squared there. 4 pi squared times LC. To find resonance frequency, you get f equals 1/2 pi square root of LC, I believe. Now, that's the frequency at which they match, where they're not like where they have the same resistance, so they cancel each other out. And that's why you see in this chart, this is where the capacitor starts off as a very high resistance. And this is frequency. So at some frequency, the capacitor will reach its resonance, and then it will start to go back up because the inductor is now starting to act more like an open circuit, and the capacitor is acting like a short. So it's kind of meeting in the middle where they both act the same exact way. Um, so yeah, let me double check that because I do that right? Did I just math on y'all? Did I just stunt on somebody? No, I'm just a ninja with a rocket launcher, you know? Your boy just cracked like that right here. 1/2 pi squared of LC. Your boy just cracked. I know. It's a gift. It's a gift. Man. But anyway, if you wanted to solve, oh, well, actually, let me go ahead and solve this for y'all. Um, so you take L, which is 15 millihenry, multiply that by 3 picofarads, square root that, multiply by 2 pi. Okay, I want to make sure I get the same answer. Multiply that by 2 pi. 1/2 that answer. That gives you 750,000 750,000 hertz, or 750 kilohertz approximately. It's a little bit more than that, but around there is where you get resonant frequency. And yeah, so that's all this math is just proving that this is true. Um and at those frequencies, your inductor and your capacitor should be equaling around the same uh, reactance value. Let's see. Different caps are used at different frequencies because of this exact reason. Um, rewrite this real quick because y'all cannot read that. I can barely read that. Yeah. Okay. The surface mount chip inductors have much less inductance. Find the resonant frequency of a. Oh, hey, I just showed you how to do this. You see, look, man, I ain't need a nose for that, man. I'm cracked, bruh. Just straight crack. Uh, what is the total reactance? So if you want to use these numbers, you can. I personally don't care. Test it yourself. Um, what is the total reactance at 10 megahertz and at 100 megahertz? So I just found those with the values that were given over here. So yeah, if y'all want to try it, try it. I promise you can do it. Y'all are smart. Like I said, y'all watching the Kristen Ninja live stream. Of course, y'all are smart. Um, and this is what a inductor looks like, I believe. Yeah, this is what an inductor looks like as its actual circuit. Self resonance. When the capacitor hits, it's a steep drop. Um, here's the math for this thing over here. Um, that's just a bonus extra problem. Let's see. What do we do this day? Parasitic inductance and capacitance. So to find that, you use you approximate for inductance using this equation. Uh, it's the same as the one that was like 2 pages ago. This is the same resistance equation from like 2 pages ago. Capacitance, you do pi times epsilon naught times the length divided by natural log of the distance between and the radius of the wires. That gives you the parasitic capacitance. Um, the freak. Include per, per to I have no idea what this says. I'm gonna keep it about. I have no idea what this says. I'm gonna have to ask one of my friends what we wrote that day. um, this is beta. Beta is 2 pi over the wavelength. That's another equation you should memorize thoroughly. Um, you want to use shorter wires to make parasitics negligible. Um, then we got into waves, spectral analysis. That's just fancy words for um, checking the thing here. Uh, defines a material. The conduct. That's what I was trying to find the word for. Conductivity. The opposites of resistivity. You want to find the conductivity, the dielectric content, and the permittivity. So permeability, permittivity, conductivity, and dielectric constant. Um, yeah. So let's see. Anything else on this page? Nope. Nothing else I can teach you on that page. Propagating waves. Basically, that's any wave that moves through time and space. Um, like my voice, the sound of Krista Ninja is propagating through your room as well as my room into your ears. That light you have on that your mom told you 15 times to turn off before you go to bed, that's propagating a wave of light into your eyes, into the hallway, into your mom's room where she can yell at you, turn that light back off because I paid this dang electric bill. Just saying. Yeah, just saying. Center point in space. Yeah, so in this class, you have to work with cosines. Me personally, I got beef with cosine. I mess with sine. Give me sine all the time. But I mean, I guess cosine's all right. Just shifted 90 degrees. Um, oh, I was trying to figure out what the heck that said. I was like, what is that? What is this like Greek? Yes, technically it is Greek, I think. I think cosine's Greek. Is it Greek? I don't know. I know beta's Greek. Uh, cosine omega. Oh, freak. I think okay, yeah, cosine omega t. There we go. That's equal to the constant. Um, this equation essentially makes it where you can find velocity as omega over beta. So 2 pi f over beta or 2 pi f over 2 pi lambda over lambda, 2 pi f over or 2 pi f lambda over 2 pi. And then that just comes out to be f times lambda equals velocity. Now that equation, that's going to come in handy too. I'd write that equation down right when the test starts if it's not given. Um, Lambda is velocity over frequency. You get that from literally this lambda velocity divided by frequency. Get that, bam, get that. Uh, Again, here's where mu r, mu naught, and epsilon r and epsilon naught come in handy. Velocity is 1 over the square root of mu times epsilon. You need that mu naught permeability. Let me rewrite that permeability of free space because y'all need that. You need it. You need it. It's so important. It is so, so very important. This is the permittivity of free space. They're like twins, but you got to be able to tell them apart. I have a good friend. She's really cool. She's a twin. I've never met her twin, so I don't know if I'd be able to tell them apart. But apparently, it'd be a lot easy. It's a lot easier now because uh, that friend lost a lot of weight. Apparently, the twin did not. But I mean, I'm sure they both. I mean, they're both. I mean, the one I know is like she looks nice. So I'm sure her twin also looks nice. Mu and epsilon are like Mu and epsilon are like fraternal twins. Like you can definitely tell them apart. Again, equations written down right here. You get write them, know them, learn them. Get that stuff down pat, down pat. Most propagating waves are since they are electromagnetic waves, propagate at the speed of light, which is 3 times 10 to the 8th. It's actually 2.999. It's like 2.997 something 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 times 10 to the 8th. Just round up to 3. You're not gonna when you're moving at the speed of light, you're not gonna miss much moving a half of a millisecond faster than before. Like you're not gonna miss much. Um, so I mean, like you could find this uh final velocity c, which is the speed of light divided by epsilon r, gives you the velocity propagation. Velocity factor. It's the percentage of the speed of light, like how much it slowed down. So I mean, the velocity you have divided by the speed of light, or 1 over the square root of epsilon r. Yeah, epsilon r. Uh, let's see. Transmission lines. Transmission lines. Honestly, I don't have enough time to touch on all this stuff, but I did touch on it in a previous live stream when I was studying for the final for this class. I touched on it in the previous live stream, so go check that first one out. I think it's in that. I think it's in that video. Um, but I'm gonna go ahead and head on out. I hope that you learned something useful. If you already knew, I hope it helped you study. Remember what you're going in there for. This professor at A&M is one of the most fair professors I've ever met in my life. Nothing comes easy in his class, but also he won't let you fail as long as you're working towards success. If you're working towards success, you will not fail. Now, if you slack off and you don't answer questions and you're missing quizzes and skipping out on the homework and stuff like that, he can't really help you with all that. But if you answer a question and you're off by a little bit, or you say like, "Oh, professor, I realized that um, I made a small mistake here. This is where I messed up. He'll or like quick little story. I was taking his class. I got like a 40 a 46 or something like on one of his tests. I was like, golly, man, I'm stupid. Look at the answers. I was like, wait a second, hold up. This is nowhere near the number that I got, and I can prove my answer's right. I go up to him. I'm like, hey, professor, I solved this a different way, and I got a different answer. And he said, all right, try it your way over the weekend. If you can prove to me that your answer is still, if you can prove to me how you got that answer, because I just couldn't understand your thought pattern from it. If you can prove to me how you got your answer, I will give you the points back. And I said, bet. 5 minutes before class started that Monday, 5 minutes before class started, I scribbled down on a piece of paper how I solved that problem. And like I actually did the calculation. I did it the same way I did it before. I figured out what I was trying to write, and I realized something. Half my answer was right, but the other half I was off by about 2 volts. I go up to him. I'm like, "Hey, professor, here's my work proving that it. Here's my work proving what I did. I realized I was off by 2 volts on one of the parts of the question. So I understand if you don't give me the full points back. This man gave me the full points back. Praise the Lord. That's all I can say. Praise the Lord. So he's one of the most fair professors you'll ever find in your life. If you have something where you can prove that it was something that you could easily fix, or that you could prove that your way is right or that your answer is correct or something like that, he will give you the points back. He'll give you them points back. I'm telling you, for real, for real. So don't worry about it. And I'll see y'all in the next one when we going over Smith charts. I know y'all gonna have fun with them Smith charts right there. I had so much fun. But that being said, I want to say thank you guys so much for watching this video and this live stream. If you liked it, if you learned something, give the like button a nice slap in the face. Like our first, subscribe to join the Shinobi Force, and I'll see all you guys. Oh, hold on, let me get ready to like actually end the stream. Okay, here we go. And I'll see all you guys. Well, what do we fly fast cars on the wall next time? Have a good night, and good luck on the tests or in your classes or in whatever else you're learning and watching this video for.